Hello everyone and welcome to this webinar. My name is Fatih Aboukshem, Research Associate at Teesside University. In this webinar, I'm going to present the decision-making and DR optimization toolset developed by Teesside University within the eDREAM project activities. The main functionality of the decision-making and DR optimization toolset is to provide the aggregators and energy retailers with toolset that enables them to utilize their energy resources in an optimal way. In recent years, the transforming of traditional power systems from centralized electrical power generation plants operated by large utilities toward clusters of distributed generation networks has received a great deal of attention by the power providers over the globe. These distributed generation networks are termed as virtual power plants. Virtual power plant is defined as a network of decentralized medium-scale energy generation units treated like one single power plant. As can be seen from the figure here, the units aggregated on the virtual power plant can be wind turbines, solar systems, and combined heat and power units, as well as flexibility offered by prosumers participating on the DR programs. The toolset consists of two main models, decision-making model and virtual power plant optimization engine. The decision-making model provides the virtual power plant managers with the optimal amount of the power reserve that is needed to balance the fluctuation comes from the renewable energy resources and the flexibility provided by the DR programs. Once the power reserve has been calculated, the virtual power plant optimization engine will provide the virtual power plant managers with the optimal dispatchable schedule of the generation units participating on the virtual power plant. The output of the engine will be the optimal list of generation units which should be used and the set points of each selected units, which satisfies the power demand and the power reserve. The general structure of the toolset is as shown in this figure. The tool uses the output from other components of eDREAM platform. These components are prosumers consumption production forecast, prosumers flexibility forecast, prosumers baseline estimations, and historical data related to the prosumers from database, as well as dispatchable generator data, which is also from the database. These data are used by the tool to first estimate the uncertainty of the PV generation forecasts and the uncertainty of the flexibility estimation, then make decision for the reserve and do the optimization. The output of the tool will be optimal scheduling of the dispatchable generators, aggregated virtual power plant PV power generation forecast, and aggregated virtual power plant flexibility estimations. For the uncertainty of the PV generation forecasts, the forecasts obtained from the production forecast component are deterministic, which means only a single value in each target hour is provided. Thus, the tool, and based on the historical PV generation data and past forecast data, calculates the forecast error and estimates the prediction intervals. For the uncertainty of the flexibility estimation, the upper and lower bounds of the flexibility of each prosumer are obtained from the flexibility estimation component. Using these limits and the baseline estimation, the tool estimates the flexibility of the VPP and its prediction intervals. Based on the uncertainty analysis of PV generation forecast and flexibility estimation and the risk index selected by the operator, the decision-making module will calculate the power reserve, which is then used by the optimization. The idea of the optimization is that the optimization algorithm will select the optimal set of generators which generate the required demand and also able to ramp up and down to balance the variations of the PV generations and flexibility provided by DR programs. The optimization problem is formulated as a customized unit commitment and economic load dispatch problem, and the objective is to minimize the fuel cost, where in unit commitment optimization, the operation schedule of the dispatchable generator is evaluated, which means identifying which generation unit will be on and which will be off. Then in economic load dispatch optimization, the set points of these units are calculated. As the independent variables of unit commitment are discrete and the independent variables of the economic load dispatch problem are continuous, and algorithms which can deal with both kinds of variables is needed. Or we might use two different algorithms, one to solve unit commitment and another one to solve economic load dispatch problem. To solve the optimization problem, a series of optimization mechanisms based on GenOpt optimization program and the method of Lagrange multipliers, and priority lists were developed. GenOpt is a generic optimization program developed by Lawrence Berkeley National Laboratory, University of California. GenOpt has a library of various optimization algorithms such as generalized pattern search, particle swarm optimization, hybrid global optimization. However, not all algorithms of the GenOpt program are able to solve problems include both discrete and continuous variables. For this reason, and to use the full capability of the GenOpt, another two optimization methods has been implemented. Lagrange multipliers, which is used to solve the economic load dispatch problem, and used with the GenOpt algorithms, which can solve problems with discrete variables. The other method is the priority list, which is used to solve the unit commitment problem, and used with the GenOpt algorithms, which can solve problems with continuous variables. A user interface works as a supervisory program that controls the operation of the optimization engine was developed. The interface also provides a user-friendly environment to use the GenOpt program, which is not present with the current versions of the GenOpt software. One of the main objectives of the user interface is to create an algorithm selection framework that acts as a decision support system to help the operators to take the most advantage of the GenOpt program. In the remaining time of the presentation, I'm going to run a quick demonstration of the toolset. We start the optimization by selecting the method. We have three options to choose, either GenOpt, priority list GenOpt, or GenOpt Lagrangian method. If we choose GenOpt to solve the optimization problem, this means that the GenOpt will be used to solve both unit commitment and economic load dispatch problems. In this case, only the algorithms which is able to solve problems with mixed, discrete, and continuous independent variables will be enabled. If we change the selection to priority list GenOpt method, then only the algorithms which is able to solve problems with continuous independent variables will be enabled. Once the optimization algorithm is selected, its configuration and settings will be uploaded. These settings can be easily amended and changed by the user. After selecting the method and the optimization algorithm, we need to upload the data. 5 files need to be uploaded. Generators data, loss coefficient of these generators, demand curve, flexibility estimation of the prosumers participating on this VBB, BFE forecast data, and historical BFE production data. To start the optimization, we press the Start Optimization button. The GenOpt program will start. It will generate the independent variables, send it to the model, and reads the value of the objective function. Once this completed, the cost and set point of each generator at each time slot will be displayed. The output of the optimization engine is shown in this screen. On each time slot, the power demand, the minimum cost achieved by this algorithm, and the set points of the generators are shown. The results also are presented graphically on the user interface. At each time slot, the set points of each generator and the cost are presented. And that is the end of the presentation of the decision making and DR optimization toolset. I have presented its objectives, structure, and demonstrated its functionality. Thank you for listening. Are there any questions?